All right, this is the video for all the Python code that will be used for the homework assignment, and also what was used to create a few of the visualizations that were seen in the presentation slide deck. I will be walking through the code and talking about how we would answer some of these questions. So first, we'll be importing our packages, always at the top, and we hit run. Some of the new packages you might not have seen before is something like math, scipy, and numpy, and these will allow us to do some of the more statistics-based things. We've seen pandas before, which is for working with data frames. Random is new, and we'll talk a little bit more about why and when we would use that. We've seen matplotlib before and seaborn, and those are for plotting. And this is another plotting package, part of matplotlib, but that's just for using to annotate our graphs. So at the top, I give a header of what will be in this notebook. And first, let's go through that example of the growth versus value, which I download directly, making sure it's reproducible from the textbook. I read it in and save it as a data frame variable. So always it's good to just see what's in this. And we have all of the years. We have the annual return from growth and from value. So let's just also see the shape. So we have those 36 yearly cycles of the annual return. In order to visualize this as a time series, you can create an index from the year. And pretty much all that does is allow the x-axis to now be the year, without needing to do much manipulation outside of that. So once we say, instead of having the index be just 0 all the way to 36 for each value, we're going to make the index the year. And I use that saying set index, and this in place just says, do it and save it to the data frame. If I didn't have that, it would actually return, oh, well, now it's not in the year anymore. So let me read that in again. We see what it looks like. And if I do without in place, we see that it returns a data frame, which means nothing was saved. If it returns something, it's not, it's just an output of whatever you did. But when we have in place, we see nothing's returned, which means it actually saved it to the data frame variable. And now if we run this again, we see the year becomes the index. And this will allow us to have that nice horizontal time series. So play around with what would happen if you didn't do that, and see what the result will be. Next, we have our plot, which now you're all familiar with how we start to plot some of these things. This is a line plot technically. And I say plot the growth column here, plot the value, make one blue, make the other red. And this says, and that's B and R for blue and red. And this gives the legend location, which this is more for aesthetic purposes than anything else. I always have a title, the X and Y label, and then we show the plot. So, and I have my description below it of what it is that we're seeing. And the reason to visualize it, it helps us now understand when we say the means are different, what that actually would relate to when we start to thinking about the central tendency. So let's analyze that central tendency. Here is a function I wrote where I know it's a function because I have this def or define, similar to that introduction demo for Python. You would see something like this where I have a comment right below that says, what exactly does this function perform? And pretty much it takes a list of values and it'll take the sum of all those values. So all of the annual return for one of these columns and then divided by the total. So that's just the simple calculation for how we would find mean. And now I apply this function to the column I want. So if you ever wanted to take things out and see what it is that we're actually applying this on, it's going to be the annual return over this time range. So we're going to be adding up all of these numbers together and then calculating by the length of this. So let's just see what that is. If you ever want to know how things work, again, just like take each part apart and try to print out what it would return. So we see we're going to take the sum of all those values and divide it by the length, which was 36. So I'll delete that row for now since it was just for our own understanding. And because we have return, it's going to return that amount, which again is the average or the mean. And we're going to save that to the variable of growth mean. So if we wanted to see what that looked like, here's how it could be printed, where I'm rounding that value to 2 places. And that is just, it makes it look nice. It's not essential to have that. You could have left it without that, but you would have a very long decimal place. So this just rounds it to 2. So the average return is 15.76%, where let's see the value fund and see what that return looks like. And the average is 12%. And please refer to the slide deck for talking more about what this all means. For now, we're really just looking at the code. And let's plot what this might look like. This is pretty much the same exact thing we saw above, but now I'm going to plot a horizontal line for the mean of the growth fund and the mean of the value fund. And that is the only difference. Now we're going to just overlap those around each other, and we will annotate what it looks like. So this again is not super essential, but it helps for interpretability. We're pretty much saying, get me all of the labels and put it where I want them to be on the growth mean, to say this is what it is for here. That's just on the left. So we see the mean value is 16 versus 12. But again, not super important. Even just seeing how those means compare to each other is good on its own. Rather than using that function that I wrote myself, Python has this handy method where it's just .mean. So now we can use that rather than write a function and call it. So anytime we have a list, we can just use .mean and we will have that average calculated for us. Let me add that. Okay. Next, if we want to visualize the distribution, we're familiar with this now using .hist, which shows the histogram. We have density equals true, which actually gives more of a proportion rather than the frequency itself. It's more of a relative proportion. We're making this red. Alpha is how transparent things are when things start to stack on each other. It'll just be more transparent rather than being opaque. And we would label this value, and similar for growth, we're saying plot these, and we're going to plot them on the same axis. So now we'll start to see how those different distributions compare in the same way. And we have our labels, of course. So having that alpha of the transparency, now we're able to see from in front to back behind, where now we can compare the difference between value versus growth, and we can start to see the similar dispersion throughout all of the sample period. Next, let's talk about calculating median and mode. This is, again, I'm going to consistently create a function that does the actual calculation so you can see bitwise what it is that we're calculating. And then, of course, Python has different methods that you don't need any of this. So we'll just have it print. But I want you to understand what it is that we're doing when we say median. And we're going to do that by showing the actual calculation. So as I mentioned in the slide deck, we want the median value, which is the middle one. So we would sort all of the values and take the one that falls in the middle. So similar to what we learned in the last class around sorting the column, this just sorts the values from smallest to largest. We calculate the length. This gets into some more advanced Python of writing if-else functions, but that pretty much says if it's an even number where we won't have exactly one value in the middle, let's say we have 4, what's the middle value? It's between 2 and 3. So we would take those 2 and then divide by 2. So we just take the average between, it would be 2.5. Else, if it's an odd number, let's say 5, like 1 to 5, the middle value would be 3. So we can just return that. And this takes that middle value. So we calculate this, and now I say find the median. Oh. We got an error. What's going on? Okay. Let's try to figure out why this isn't working. Find median. We're going to have this go in there. It's because it doesn't like seeing let's see how this works, where we just have just the values rather than the column itself. Okay, nope, that didn't work. Okay, so let's see where we're going to troubleshoot together here to see where the issue lies, because this actually isn't really being very helpful to tell me where the error exists. So let's just see if we get to here, if we can print n. And this is always good just to see like where does it mess up. So we were able to print n. And because it's an even value, it'll go over here. So this checks to see if it's divisible by 2, making it 0. So let's just see print. So we know it went there. And let's see what happens there with key error. I don't know why I'm getting that. So let's see if we can print these. One. Again, I'm just doing this so we can see where exactly the issue lies. So it's not even letting us print these. So maybe there's something going on here. So it's not calculating this, which let's just see what this would do. Where let's walk through this with the sort values of what this would look like. So we take this data frame, this column, we sort the values. Now we see the lowest to the highest. And since it went into this category where we know it's an even number, since we divided the remainder by 2 and that equals 0, so that means it's even. And let's see, I think actually, I don't know why these have 2. I don't think that's right. I don't know why that happened. Because we would want to take the middle value when we are taking the index of the length, which is here. So we know that's 36. So we're taking the 36 divided by 2 because we want the value right in the middle, which would be 18. So, okay. I think that's the issue because we're not having it as, okay. Maybe I think I need to look into this again because we just want the 18th value. Let's see. I think it's actually because of our index here. Since we have the index as the year, I can't actually say, get me the index at 18. Because the index 18 is really now index whatever year that would be in this scale. So the way we're going to troubleshoot this is by reloading that data frame. And I think we found our solution. So so that way we can have the index be, well, actually, we don't need to read it back in. Let me do something called reset index, which, as we see, when it returns, now it'll go back to where we were before, where we have an index. So now we can say, get me the 18th index. And because it returned, it didn't actually save it there. So let's now write in place equals true. So now let's see. This error is telling me we can't do it on a series because I wrote that on just this column because we want to reset the index of the entire data frame. So I don't need to say just this column because the data frame, we can't reset the index just on one column. It needs to be the entire data frame. So now we don't get an error. And let's see, just to see when we take the sort values and take the 18th, now we get it to return. So let's see what happens when we run. Great, now it works. We were able to figure out the issue and you were along for the ride to see how we might troubleshoot something like this. So let me remove my print statements since it was more so for understanding what's going on in the different spots. And you can see I made this a while ago, so we're revisiting it now. We always might run into some of these things. So I'll just reload that, and now it should only print and return the median value. But if we didn't want to go through all this trouble, and for your homework, you can just use the method of dot median rather than using what I defined myself. Actually, let me, because that's not the same. I think I did need these, but I forget how that changes things. Let's see. Nope, this isn't right. Yeah, something's off with the decimal value. If anyone can find it out, we can talk about extra credit. But for now, just use this median method, and don't worry too much about using this formula. I really just wanted to show you what it is we're doing, but I think it caused more trouble than it's worth. All right, so if we wanted to create a same custom function to define the mode, this is another way we would do it. This is a package called counter, which pretty much just counts how many times an instance would happen. And we take the length and this counter object. So let me just show you what that looks like when I print what I'm saving this counter item as. And we will save a dictionary of that. So we'll be able to just find the highest value. And we obtain the maximum by getting each value of that dictionary and saying only when it's the largest value in that is the maximum. If the length of the mode that we find here of that maximum is equal to n, that means all values are the maximum. That means there's no mode. Else we'll have that mode show. So out of all of these, is there one that comes up the most often? No, there's not. That's why this returns the same. None of these show up more than the other. If we had a categorical variable, that would be more interesting, or even just like a round numbers. But for now, since we have all these decimal points, there's none that repeat itself. But mode is relatively a weaker form of central tendency anyway, mostly because of something like this where it just doesn't show up too often. But if we rounded these, maybe that would be more helpful. So let me just show you what it would look like. Let's just do test of 5, 5, 5, 6, 1. And I'll write example for mode when there is one. So if I were to do test.mode, let's see. Okay, well, we need this to be a data frame to be able to use. Let's just make this to be able to use the pandas mode. So let's make this into a data frame. And we see the mode. So by just writing pd.dataframe, it turns our list into a data frame. And now .mode returns that 5 is the mode that comes up most often. If I wanted to use my handmade function, let's see if it returns the same thing. And this is that counter object so this is what I really wanted to show you, because it shows for each value how often it shows up. And then it takes the value that showed up the most and returns that. So we see 5 came out 3, 6 once, 1 came out once, and it knows 5 was the max. Moving on. Let's talk about other descriptive measures. Something like describe is very handy to give us all of these different information points, such as how often does it show up, what's the mean, what's the standard deviation, what's the minimum value, what's the maximum value, as well as our different percentiles. So this is like a one-stop shop to really get a good understanding of the entire column. And the value like year isn't very helpful for us to look at, since it's that type of scale of data that isn't actually informative of a value that can really be compared. So other functions we can use to get these same things, if we just wanted the maximum or minimum, we can use these different methods of .max or .min. For percentile, we use numpy, which we imported as NP. And that'll say for this column, return the 50th percentile, which is also that middle value. So even if we didn't want to use that median or .median, we can take the percentile at 50, which would give us that middle value in the same way. So lots of different ways we can come to the same answer. When we wanted to calculate that mean absolute deviation, this would be the formula where we take the mean, we have the length of the data set. I make a list that's just empty, where now for each value in this list of our column, we're going to add the absolute difference between that value from the mean. And then we take the sum, which we saw in the formula sheet from the slides, is that big sigma. So we add up all of those differences and divide it by n. And there we have the mean absolute deviation for the value stock and for the growth stock. But again, rather than writing your own function and doing it like this, Python has the handy function .mad, and we'll get the same result. Next, for variance, how we calculate variance, we take the mean, we have the length or how many samples there are, or a value of n. Similar to what we had above, we just have an empty list. And for each value in this column, we're going to take that value, subtract it from the mean, and take the squared difference. So compare these two different formulas where one had the absolute, the other one has the squared difference. And then we're going to return the sum or the sigma of all of those differences and divide by n minus 1. So we'll show that here. Now we know the variance, and we can also then use that built-in function called .var, and we'll get the same thing. And I wrote here what the takeaway is from what we just calculated. Next, for calculating standard deviation, we have the mean, we have the total sample size. Again, very similar and to what we just calculated for variance. The key difference, though, is that we take the square root of all of those sum differences, and that then brings it to the same unit that we can now compare. Because something like this is a little less interpretable than when we see the standard deviation to say it varies by 17% annual return. Now we have it in the same unit that we have our mean in. So it's a little easier to use as one standard deviation above this and below. What would that equal compared to variance, which looks at like the overall dispersion. And again, rather than using our handy function I just made, I can use this STD, standard deviation, from Python. So I showed applying my function to the data frame column growth. And here I show how it would look like just using the function. And so for your homework, again, just to reiterate myself, feel free to use the simpler version of just using the Python. I do want you to go through some of these formulas just so you understand how they work, especially when you can then compare the differences where the code is all the same except for one little switch. So you kind of actually get to see how these formulas work. When we say standard deviation, we know what's going on under the hood, which is important to not just throw a number, but really understand how did we get here. And here I have my description around how we use this to understand risk. Next, for the coefficient of variation, which is just the standard deviation divided by the mean. We can also then use the built-in function. I didn't create a whole function for this, but we could have made calc coefficient of variation and just return this. But for simplicity's sake, I didn't do that because we could also use this built-in function from SciPy, the stats package, which we'll end up using quite often this semester, and taking the variation, which if you hover over, you can start to see what's in it. This computes the coefficient of variation. And we see it's pretty similar, but probably a bit more precise than what we calculated here. And we see the same thing for value. Next, we can also measure the level of skewness by using this dot skew. And seeing that it's negative, we know that the returns are negatively skewed, and we can assume that the extreme values lie to the left of the mean. So if we're thinking about that distribution, it's kind of leaning more this way. So we have this tailedness. We also have this kurtosis, which gives that measure of tailedness to measure what proportion of the data is actually in that long tail. When we think about that very symmetrical normal distribution, there is no kurtosis because the area is under the curve is symmetrical and we don't have these long tails, so it would be 0. So the higher the kurtosis pretty much means that the heavier the tail. So this does have some tailedness, which again shows us how much does this disperse beyond the mean. Next, we're going to go into an example about understanding difference between a sample versus the population. We'll consider the example of spending patterns during the holiday season, where the following data frame contains 130 existing customers, demographic data, and dollar amount spent on different categories of retail. And this will be pretty similar with the homework, the file you'll be working on. So we read this in using this sheet of online data. And let's say we wanted to calculate, let me fix this spelling mistake. We want to calculate the average for each category between male and female customers. This will help if you're doing marketing and you want to know how should you target different demographics for each product category. We would be able to know on average which demographic spends more on these different product types. So let's see what our columns are we have to work with. And now across these different product categories, I can just say group by sex. So between female and male, take all of these columns and calculate the average, the mean. And just in one line of code, now we have all of the means for every category, and we can start to now understand how these things differ. So for the homework, you'll be taking this data set and doing a lot of other things that we just talked through in this demo on the same data set. So understanding now, just seeing the difference in means is one thing, but we'll get more into all the other aspects of measuring the data that we talked about today. How we would create a box plot is pretty straightforward with .boxplot, which is pretty handy. we just say, give me the column. We have the data frame that we want to make the box plot for, and say, give me these two columns. So I didn't add a title and all the other things that you're supposed to add, but when in your homework, make sure to have those there. This just shows that little outlier we had in the value, and the different, the whiskers show how far the values range. And we see that the median is here, that they're very similar. But again, for more description on what it is you're seeing here, we'll have that in the slide deck presentation. There's also a comparable way to plot if we didn't want to just use dot box plot, which makes it a little more aesthetically pleasing, using Seaborn SNS, which we downloaded in the middle, which has similar of dot box plot. And we say the data are these two columns, and we can get a little fancy with the colors that we want to show. And I say, I want to make this horizontal, and let's show what that looks like. So again, it's just more aesthetic. So you can decide which one you'd want to use. And I have this one, I have all of my labels and the rationale underneath it. And getting towards the end here, we're going to talk about the relative location, where this was that example about the Salesforce prices, Salesforce scores, where we knew the average was 74 with a variance of, actually, I think this was more standard deviation. I think this is incorrect because it should be standard deviation. Let me change all those. So that it just makes more sense. I don't want it. We could call it anything we want. We could call that, B and just use that, but I want the consistency of what it is we're doing here. And this just shows us all of those. If we were to take -1 standard deviation, +1 standard deviation, these are all the different colors to show across the distribution of scores what proportion of the total sales force will earn what score. So we see these tails of not many people will score above 90 or below the 58, but it's still a possibility. Next, let's talk about the outliers and using our z-score. So I'm just showing we save these growth mean and standard deviations and value. Let's talk about how you would calculate an outlier just using the z-score and comparing it to a threshold of 3 standard deviations above or below the mean. So that would be, so what you have over here, these are those standard deviations, like even beyond here. So we would take one more. And the highest allowed and lowest allowed is what that would be. And our threshold is 3. So we could change this if it was a different context, we'd want to define an outlier as anything above 2 standard deviations above the mean. But in general, we would say anything 3 standard deviations above the mean is very unlikely to be seen. So that's how we would define an outlier. And for each value in our list, we're going to calculate the z-score here, which takes that value, subtracts the mean, and divides it by the standard deviation. And if this z-score is greater than our threshold of 3, or if it's lower than that threshold of 3, we're going to call that an outlier. So let's see for the growth. And we see that the highest value is 79 and the lowest value is 40. But we don't have an outlier in this data set. But for the value, we do at -46. Because in this one, nothing went below that -40. But for here, the lowest value of -46 went beyond -41. And let's just visualize this over time. We are now just plotting what these values would look like using horizontal lines after we plot the value. And we have our legend location, and this just annotates it, like what we talked about in the beginning. And now we can see above or below, and we see this value fund dips below that allowable threshold of -42 to -46. And so we can say that's an outlier because it's beyond 3 standard deviations away from the mean. And lastly, talking about covariance, this would plot the horizontal line around growth, where we have this scatter plot, and we say, show me the difference between the growth and value. And we'll see this type of, is there any type of covariance between them? Like when growth goes up, does value go up? Like, are these two fund performance returns, is there covariance here? And because it's relatively in that positive direction, we can say there's a positive relationship between, perhaps indicating that if one does well, the other fund tends to do well too. And intuitively, this makes sense because the stock market would likely differ in similar ways between the two funds. Now, if we want to calculate what that covariance value would look like, we take the mean of the first column and the second column, and we have the total length of the data set. It doesn't necessarily matter which one we took because both of them are the same length. We're going to create a list, an empty list, and then for each value in going through each pair of X and Y, so for each value of growth and value, we're going to take the subtraction similar to the z-score of like take that value, subtract it from the mean, but now we're multiplying them. So we're multiplying the differences and appending it to a list, and then we're summing, so taking the sigma across all of them and dividing by n-1. And we'll talk later about why we do the n-1 in future chapters. So we have the outcome of this. We can also use numpy.cov as a way to estimate the covariance matrix. So we would just say between these two values, let's see if it's how we would actually calculate that. And this gives the entire matrix where this value is over here because that's the one in both. These, essentially, this takes the covariance of growth against itself, and this similar with value against itself. But because we're looking at growth versus value, we would take the value that's along the diagonal. And now if we wanted to show what this looks like, because this chart makes it difficult to really understand, that's what we would do here. And so we see that the covariance we calculated of 285 when X is considered growth and Y is considered value. And we also then see just those other combinations that I talked about before. That's what you're seeing in these other boxes, is growth against itself and value against itself, which doesn't really give you much information you actually want. Next, if we wanted to calculate the correlation, let's change this because you can see I just copy and pasted most of it because it's very similar, but we're not calculating the covariance, we're calculating the correlation, which we take the means as we showed before. And now for each of those differences, now we're going to, the main difference is that we're just dividing that correlation. Actually, no, it was the covariance. So we could have, that is the covariance. It's the same exact thing we had above. But now if this was more specific, I'd say the correlation equals this and return correlation. So let's do that just for being explicitly obvious with what we're doing here. That we take this covariance, which is the same exact we calculated from the last formula, and we divide it now by the standard deviation multiplied by both columns. And then that's what we're returning, which is the correlation. So that's why it's good to just be very clear with what it is that gets returned. So that's why I added that. And now we can start to see this correlation. And again, we can't assume any causation. This could be a spurious correlation, like with the example we talked about in class, that there is no necessarily dependence between value and growth. They're just similar when they perform. So we can use this dot core value, which again, similar to what we had above, where it shows the covariance against itself. You know, growth is correlated with itself exactly. And that's why it's not very meaningful as one. But what we are looking for is this value, which we calculated using our formula above. If we wanted to plot what that looked like, we can use this heat map, and we see those values here. So now you will have all of the code necessary for performing the homework assignment. So feel free to ask any questions on Slack, and looking forward to seeing you next class.